Your turn now, Professor Halozan from the Institute of Thermal Engineering dell'Università di Graz. And title, Heat Pumps, Reducing Losses, Increasing Efficiency. Please.
Ladies and gentlemen, I will make it also short. I get 10 minutes, what I know. And we have talked tomorrow a lot about direct losses of heat pumps. We should also talk about indirect losses, and these indirect losses are the major losses in all refrigeration technologies, and they also contribute to the greenhouse effect. It's the power generation for driving refrigeration equipment. Now, that means this refrigeration equipment has to be as efficient as possible, and we have this problem with the greenhouse effect. We have these temperature fluctuations. This is a graph since the last 450,000 years. And as you can see, we always had temperature fluctuations in the long term. Now we are not at the highest temperature we already had in the past, but we have a CO2 content in the atmosphere we never had in the last 450,000 years. That's our problem. And this is a nice idea. This also had the European Union. They they formulated the famous 20-20-20. That means 20% less CO2 emissions, 20% less primary energy, and 20% share of renewable energy, representing global warming, economy, and security of supply. Now, in such a case, we can use very good Carnot, who has investigated the right turning cycle for power generation and who has theoretically invented the refrigeration cycle used for cooling purposes or for heat pumping purposes. In principle, it's the same machine with the most commonly the same equipment and the same refrigerants, by the way. If we go in the heating mode and we take an outside air heat pump, an outside air heat pump has a very nice characteristics, and this is a exergy diagram of such an outside air heat pumps, depending on, I hope it works somewhere, depending on the heat sink temperature. That means the heat sink outlet temperature, the heat pump outlet temperature, and the heat source inlet temperature. And as you can see, this heat pump has somewhere its optimum. In this case, it's about 0.43, that means 43%. And this efficiency drops with higher and lower heat source, heat sink temperatures. Here the optimum is around 0 degrees centigrade with about 42 degrees centigrade heat pump outlet temperature. And you can modify such a unit, and this unit is based on all the parasitic losses. That means in this case the fans for the outside air heat pump. In this case, not the circulation pump, the compressor control and all these things. And if you start improving such a unit, you can raise the efficiency to more than 50% presently. In the case of a vapor recompression system, a mechanical vapor recompression system, you can go up more than 72%, because you avoid one heat transfer loss on the evaporator side. If you take the climate, that's the solar radiation, that's the resulting temperatures, you get the temperature pins for the operation of such a heat pump in the heating mode, and this is a colder climate, it's Central Austria somewhere. And you can see you have the average somewhere at -2 degrees centigrade. You have minimum temperatures of below -20, and the heating boundary is somewhere in the range of 20 degrees centigrade. And if you integrate now an outside air heat pump directly in such a circuit, you can see that the load, which starts at about 15 degrees centigrade, rises up to its 100% value at -22, and the capacity of the heat pump is remarkably higher. And this remarkably higher capacity means that the heat pump outlet temperature is significantly higher than the temperature required by the heat distribution system. Here is again the return temperature, the heat pump outlet temperature, and this is the required temperature by the heat distribution system. That means you have, of course, cycling losses on-off, and you have these excess temperatures, which costs a lot in COP. If you want to improve this, you can do it by introducing a buffer storage. That means decoupling the heat delivery by the heat pump and the heat use by the distribution system. And if you increase the flow rate through the heat pump by a factor of about 2, then you can see that the capacity does not change here on this side. However, what changes is the excess temperature which the heat pump produces. That means it's a significant increase in COP, or SPF in this case. You can also make a nice arrangement, 3 heat pumps in series on the heat sink side and in parallel at the heat source side. Then you get a further increase due to the fact that the heat pump heat up the heating water in steps. And if you take these rotary compressors and also other ones with permanent magnet, brushless DC motors, you get high efficiency and you have the possibility for speed control. And if you take this, you can adapt over a relatively large range the heat pump outlet temperature or the capacity of the heat pump to the load required by the building. There are, of course, also other possibilities to increase the efficiency of a heat pump, and that are the different ways of two-stage compression. The real two-stage compression on the left side, the economizer flow sheet on the center side, where this part here, this is usually one compressor, or the refrigerant cascade, where you can use 2 different refrigerants adapted to the temperatures required. And if you take the economizer with the one, you can use a scroll compressor with additional gas suction ports. And in this case, you can increase the capacity, that's the one step, and the other thing, you can also increase the COP of the unit, especially at low temperatures. That's a very important way to increase efficiency. Another way is, of course, you go away from the outside air, you go to groundwater or to the ground with a very stable temperature, and over the year, a higher temperature than expected from the outside air. And with such a way, you have also the possibility to integrate it directly with these excess temperatures, however, much, much lower than in the case of an outside air heat pump. Or you can also take a variable speed heat pump, a variable speed heat pump, and here you can adapt the capacity over a wide range to the load of the heat pump, which means extremely high efficiency. And in such a case, you have again 2 possibilities. If you make a ground collector, that means if you have also to consider the heat transfer from the ground, which is in this case a store, to the refrigerant, by reducing the capacity of the heat pump, you increase the evaporation temperature because the temperature loss from the ground to the refrigerant can be diminished. And these are some possibilities with horizontally installed collectors. By the way, this is a unit with propane as refrigerant for outdoor installation. Or in vertical systems, there you have also the possibility, if you have capacity control, you can reduce the heat flux to the coil and you can increase the temperature to the coil, which is an important measure to increase the seasonal performance factor of such a system. Or you can also take, instead of a circulation pump, a CO2 thermosiphon which delivers heat without pumping requirements to the evaporator of the heat pump. A next step in this thing are the so-called passive houses, and in these so-called passive houses a lot of modification has been made. Strictly, you should not call it passive houses, you should call it ultra-low energy houses, because some of the rules of the passive houses are no longer valid. And in this case, you again have the possibility to combine a ground source heat pump with the ventilation system and to make a fresh air heating system. And the common value requested from the passive house producers is 15 kilowatt hours per square meter and year. And if you take such houses and you include photovoltaics, you can form a so-called net zero energy building. And this goes in a way that the first electricity for a conventional house is imported. And if you increase the production of electricity by photovoltaics, if you add maybe solar thermal, you can come to the so-called net zero energy house, or even an energy plus house. That's a very important step in the further development. And the funny thing is, if you take now the results, this is a strategy study of the IEA from 1980. They stated that the only part where you can reduce in a relatively short time the energy demand is the residential part. And in this residential part, they had a prognosis of a part solar, a great part heat pumps, and a part district heat. In the meantime, the IEA has made a new study, and in this new study, the result, in this case for 2050, is very similar. The upper two things are combined heat and power. The next part is solar, and the last part are heat pumps. That means it has not so much changed. Thank you very much.
Thank you very much.